Alright, welcome back. Now let us continue with our second part for deformation of solids. Now this is a stress strain graph for a ductile material. What is actually ductile material? I will explain more about ductile material. Okay, but first of all, let us look at this graph. This is a very important graph in this topic. Now, you see the first part, okay, from O to A. From O to A. A is called the limit of proportionality. Limit of proportionality. That means when the wire is being pulled by a certain stress or force, when it's being pulled by a certain stress or force, the wire will elongate with elastic deformation. Elastic deformation means it can return to original length. Yeah, elastic. You know, you still remember the elastic, like the rubber band, very elastic, isn't it? Elastic, that means when you pull and you release the rubber band, it will return to original length. That's called elastic. Yeah, elastic, like a spring. You can never change the original shape. Like a sponge. Sponge also elastic. When you squeeze a sponge and you release the sponge, it returns to original shape. Or the spring. The spring, when you pull the spring, you release the spring. When the force becomes zero, the force applied becomes zero because you release the spring will return to original length. That's called elastic deformation. So the first part is the elastic deformation. That means for elastic deformation, we have a limit. We call elastic limit. Elastic limit. So before, mind the word, before the elastic limit or until the point of elastic limit, that's the limit for elastic deformation. What's meant by elastic limit? Elastic limit means the limit for elastic deformation. That means if you pull the wire until, that means your stress increase. When you pull the wire, you apply stress to the wire. Yeah, to the metal wire. You apply stress to the metal wire, the stress increase. So until the limit of elastic limit, the wire still undergo elastic deformation. That means if you apply the stress until the point of B, which is the elastic limit, you pull until B and you release, it surely go back to original length. It surely go back to original length. So that means the strain, when your stress increase until, let me just show you like this, yeah? If you increase the stress until this point, the elastic limit, the point B, okay, until this stress, so the wire will elongate until this strain, elongate till this ratio. But when you release, the stress becomes zero again. Yeah, stress becomes zero again. When you release the stress becomes zero. The strain also will become zero again. The strain also will become zero. That means no more elongation. Because what is strain? Strain is actually based on elongation. When elongation becomes zero, strain becomes zero. Understand? So when the stress becomes zero, elongation will become zero. That means basically, if you elongate the wire until the point B, when you release the stress becomes zero, the wire will go back to zero. Yeah, the graph will go back to zero because the strain go back to zero. So when it go back to zero, that means strain now also becomes zero. When strain becomes zero, what it means? When strain becomes zero, it means what? Means the elongation also becomes zero. No elongation, no permanent elongation. That means it go back to original length. You understand or not? It can go back to this original length. To this original length. Yeah, to this original length. So elastic limit is the point where the maximum point where you can elongate until that elastic limit. When you release the stress or release the force, it will totally go back to original length. Okay? Elastic deformation only allows until the elastic limit. Understand? But what is the difference between elastic limit and limit of proportionality? You see, between the point A and B, the A is the limit of proportionality, B is the elastic limit. Between A and B is actually a bit curved. It's actually a bit curved. You know, understand? It's like this. It's like this. Let me show you. Sorry. From O to A, from O to A. From O to A is a straight line. It's actually a straight line. But from A to B, it's like this. From A to B is a bit curved. The curve does not obey Hooke's law. Okay? It does not obey Hooke's law. So, where it obeys Hooke's law? Where it obeys Hooke's law? Only from O to A. From O to A. So, A is the limit of proportionality, where the wire still, because O to A is a straight line. So O to A, obey the Hooke's law. Obey the Hooke's law means F equal to KE is valid. Or we can say stress and, or obey like this one, this equation. Stress equal to Young modulus strain. Okay? You know, K is actually the gradient of force elongation graph. Y is the gradient for stress strain graph. Because we are talking about stress strain graph. So the gradient of this graph is Young modulus. So these two actually explains Hooke's law. Yeah, force is proportional to elongation. Stress also proportional to strain. The higher the force, we can say the higher the force, the bigger the elongation. The higher the stress, the bigger the strain. These two equations is actually almost the same. These two equations almost the same. Okay, just the difference is this is force elongation graph. This is stress strain graph. So before the limit of proportionality, point A, these two equations valid. Force F equal to KE and stress equal to Young modulus strain valid. After the point A, the graph become curved already. It's no more a straight line. No more a straight line. So no more a straight line. These two equations cannot apply anymore. Cannot apply. Okay. But however, elastic deformation is not until point A. The elastic deformation until the point B. Point B is the elastic limit. Point A is the proportionality. Understand? Point A is the proportionality. Point B is the elastic limit. So the wire show elastic deformation until point B, which is elastic limit. That means when you pull until the elastic limit and you release the stress, the wire can go back to original length entirely. Understand? Now, what happened after elastic limit? After the elastic limit, after the point B, you pull some more to point C. B and C is showing partial elastic and partial plastic deformation. Okay, let me explain what is difference between elastic deformation and plastic deformation. Just now you learned elastic deformation is something like spring. That means you pull and release the force, it can go back to original, can return to original length. Plastic deformation is like plastic. Do you pull the plastic before? Do you take a plastic bag and try to pull the plastic before? If you pull the plastic, it will elongate. But when you release the force, it shows it cannot go back to original shape. It shows a permanent elongation there. Yeah, permanent extension already. Yeah, you pull the plastic, you find that the structure become different already. The structure become thinner. The color also change, become more pale. Because the material become thinner already, thinner. Yeah, it elongate already, elongate. That's called plastic, like plastic bag. When you pull the plastic bag, it will elongate, and cannot return to original length. That's called plastic deformation. So elastic deformation is when you pull and release and can return to original length. Plastic deformation is when you pull and release, it shows permanent extension, cannot return to original shape or original length. So when it exhibit the plastic deformation, is actually after point B, between B and C, it shows partial elastic and partial plastic already. Why I say like that? Okay, from O to B, it shows elastic deformation. From B to C, it shows partial elastic, partial plastic. That means if from point B I pull to point C, it still can go back to original shape, but not entirely. If you release the stress back to 0, the strain become P. The strain now become what? The strain now become, let me show you. The strain now become P. The strain become P. Strain become P. So it has small amount of elongation already. When you pull to C, when you release the stress back to 0, the strain cannot go back to 0. Strain can only go back to P. So P is a very small value. Yeah. So that means it has certain small amount of, it's like that. You pull, it go back to original length, but it has a small amount of extension already. It cannot go back to original length entirely. It's like the spring, spring. If you pull until the elastic limit, you release, it can go back to original length. But you pull some more, you feel like structure change. The structure change a bit. When you release, it still can go back, but it got a certain amount of small elongation already. Permanent elongation. Small amount of permanent elongation. So when the stress, you pull to C, C is called the yield point. Until the yield point. So when you pull until the yield point and you release the stress, the strain cannot go back to original length entirely, but it go back to P. It has a very small amount of permanent elongation. Okay, it's still, so that's why we call it partial elastic, partial plastic. Partial elastic because it still can go back to original length, but it also shows partial plastic. That means it cannot go back to original length entirely, but it has a very small amount of permanent extension already, which is point P. Okay, that's called yield point. Yield between elastic limit to the yield point is the partial elastic and partial plastic deformation. But if you pull some more, after the yield point, you pull some more, your stress increase some more. If you increase the stress some more, what happens if you increase the stress until this point, until the point here? If you release the stress back to 0, the wire, if you pull some more above the yield point, you pull some more, It will show entirely plastic deformation. It becomes just like the plastic bag. You never see a plastic bag can go back to original shape, isn't it? You pull the plastic bag, you never see it can return to original shape. Never. The plastic bag never shows elastic deformation. It never can go back even a little bit. No. You pull the plastic bag, it stays like that. You pull the plastic bag, it stays like that shape forever. That means for plastic deformation, after point C, after the yield point, you pull some more, the strain will stay at that value. The strain will stay at this value. The strain stay at that elongation permanently. It shows permanent deformation, permanent extension. It go back. You know, the graph just go down. The strain remain that value. It can never go back a little bit. Cannot. Yeah, it shows permanent elongation. That's called plastic deformation. Cannot return to original length at all. Okay? So you pull some more. Point D is called the breaking stress. Breaking stress. Breaking stress, it means what? The maximum stress it can. This is actually the maximum stress. The maximum stress, you know, this is the maximum stress here, this point. The maximum, show you, the maximum stress, the steel can withstand. This is the maximum stress, the breaking stress, the maximum stress, the steel can, that's the maximum already, maximum value of stress the steel can stand. After the breaking stress, after the maximum stress, you can see the wire, it cannot stand the stress anymore. It can support, elongate some more the strain. The wire will continually elongate, and it cannot stand any higher stress anymore. It cannot stand any higher stress. The stress it can stand will drop until it breaks. Until point E, it breaks. That means after point D, if the wire elongates some more, it cannot stand the stress higher than breaking stress anymore. Instead, the curve down. The wire can only stand a stress lower than the maximum stress. And you can see the wire keeps on elongate until the point E. Point E is the maximum strain. The maximum strain it can stand. After the maximum strain, it breaks. That's called the breaking point, or the wire breaks that point. Understand? So let me explain in a nutshell. From O to A, it obeys Hooke's law. It obeys these two equations. Okay? After A does not obey Hooke's law. But the wire from O to B, if you elongate from O to B, it shows elastic deformation. Yeah? Until point B, if you release the stress, it can go back to original length. The strain can go back to 0 entirely. But after the elastic limit, you extend to yield point. B to C is called the partial elastic, partial plastic. That means it can still go back to original length, but not entirely. It will go back to point P only. It cannot go back to point O. So you increase from O to B, it can go back to O. Increase from B to C, it can go back to P, cannot go back to O. You elongate after point C. For example, let's say like this point. Here. It shows permanent elongation. The graph doesn't go back. Instead, it go down over here. If elongate after point C until here, it cannot go back to the wire cannot go back to O, but the wire go to the permanent strain here. It just go down. Okay, so O to B is elastic deformation, B to C is partial elastic, partial plastic, C to E is plastic deformation. Okay, so elastic deformation means can return to original length. Plastic deformation cannot return to original length. Now, we have two types of material. One is called ductile material, another one is called brittle material. Just now, this graph is the graph for a ductile material. Why we say this is a graph for ductile material? Because it has plastic deformation. Look at this one. We have steel, glass, copper, and aluminium. You see, glass. You see or not? Which part of graph shows elastic deformation? Which part of graph shows plastic deformation? Of course, the one with a straight line, almost a straight line, is called the elastic deformation. That means when you release the stress, it can go back to original length. But the curved part is mostly plastic deformation. So what's the difference between glass and the other three metals? Glass is a brittle material. Glass is a brittle material. So for glass, it shows, you see, surprisingly, glass also shows elastic deformation. Yes, glass is elastic, but very small elastic only. Yeah, very, very small elastic property only. Glass shows elastic deformation. You pull until the elastic limit. But once you pull some more, the glass cannot undergo plastic deformation. You can never see a glass can elongate. Cannot see a glass can elongate. Cannot, yeah? The glass, once you pull some more, it breaks. It breaks just like the chalk, you know, the chalk. You pull, it just break like that. It just break like that. You can never see the chalk can elongate. Unless you dip the chalk into the water or something. But you know, brittle material can never elongate. It cannot elongate. So glass can have a small amount of elastic deformation, but it has no plastic deformation. That's the point. Glass, a brittle material, cannot plastic deformation, cannot elongate. Impossible to elongate. So glass don't have plastic deformation. But for steel, copper, and aluminium, you can elongate the steel, you can elongate the copper, can elongate the aluminium. So this ductile, we call it ductile material, they show plastic deformation. So what's the difference? You see? Which material show plastic deformation? Only the steel, copper, and aluminium. Which material is brittle? The glass. Why? Because it breaks after elastic deformation, no plastic deformation. So what's the difference between ductile and brittle? Ductile material can elongate. Brittle material cannot elongate. Cannot elongate. It just break. Cannot elongate. Actually, I can say like that. Elongate. We can say this one like elongate this plastic deformation. This means elongate lah. Elongate permanently. Why I say that? Ductile material can show the elongation, the plastic deformation. Brittle material cannot show plastic deformation, cannot elongate. Yeah, it just break. But both material can undergo elastic deformation. Okay? Brittle material also can elastic deformation, just no plastic deformation. Okay? I think that's all for this chapter. I hope you understand. If anything you don't understand, please leave a comment below and please like and subscribe. Thank you. See you again for the problem solving. Bye.